axis. And the result is you get a non-zero torque, right? So in general, right, if you have something that you twist and can exert a torque, if you have whatever it is, a wire in this case or anything else, what's happening is, if you take a cross-section of that body, that long thin thing, there are forces, right, being exerted from one section to the next of it. Like this, if you take it and you twist it like this, right, if you take each little part of it, this guy, he's exerting a force, let's see, that way on the top part and that way on the bottom part, all the way along. And at the end of the thing, where you've got this guy stuck on the end, same thing. It's at the end of the wire is exerting a force that way on the top part and that way on the bottom part, exerting a torque on that piece. So in fact, it is an off-axis, it's a force that's acting off-axis, but it's really small. It's hard to see, but that's what actually is happening. And the forces are really big. That's why it doesn't give you a non-zero torque, even though the force is a very small radial arm, right? This is the opposite of what you might think from a wrench. Wrench gives you a big radial arm, right? That's why you want to have a big handle on your wrench. You don't have to push very hard. But the sort of steel that's used for these kind of wires has a lot of, I don't know if it's tensile strength. It's actually, what do you call it? Twisting strength, we call it. I don't know what kind of strength you call it, but you stretch it and you can compress it. There's all different kinds of strengths. It's like a shearing strength, I guess. Or if you try to twist it or pull in different directions, different parts of the material, it resists very strongly and produces a large force. Anyway, it's a good question. But yeah, on the midterm on Thursday, you're going to have forces that are clearly far away. Like, well, some will and some won't. And the only ones giving non-zero torques are the forces that are not pointing straight at or not directly acting on the pivot point, right? Yeah, right. And that's the case here. It's hard to see. It's really small. Okay, so torsional pendulum, right? After that, I think probably the most important oscillator we'll learn about are pendula, right? You should just put over a pendulum, right? You've already seen this one. I like this pendulum. So it's a big bowling ball, and this is a really slow pendulum, right? The frequency is like, see, okay, 0, right? You can go get our lunch, right? 1, right? Very slow compared to those other oscillators, right? 2, right? So now if I go over to this guy, so this one's different. It's got a smaller mass, and it's also smaller in how long the length of the cord is, like 1, 2, much faster, right? But what matters? Is it the mass that matters? The thing is, this is obviously a smaller mass, right? This isn't like plutonium, and that's not balsa wood, right? These are made of the same material. So the mass of that bowling ball is much greater than this. You might think that that's what causes the difference. And in fact, this sort of encourages you to think that when you have an oscillator, if you have a mass on a spring, right? Mass is in the denominator, which sort of makes sense. And we even saw it here with the torsional pendulum, right? Where it wasn't the mass, it was the moments of inertia. When I added more mass on here, the thing its mass has extent, so I was increasing the moments of inertia about the axis of rotation. And that's why it had a smaller omega, because, and by omega I'm specifically referring to the frequency of oscillation. The frequency of oscillation went like the square root of kappa over I. And again, just so it's really patently clear, if I wanted to know how many oscillations do I get per second, I'd say, oh, the frequency of the oscillation equals, where is it? Here it is, omega over 2 pi. So it's omega oscillation over 2 pi. But nonetheless, it depended on I, which in turn depended on mass, right? But in this case, it doesn't depend on mass. It depends on the length of the cord. So why don't I prove that to you? And the way to do that is to write down Newton's second law for rotations, right? And solve this restorative sort of torque problem for a pendulum. So here's our pendulum. It's hanging from the ceiling. It's tied on up here. Here's a vertical line. Here's our cord. It's got some length L. Oh, I'm sort of breaking my rule here. I like to make these things close to 30 degrees, not close to 45 degrees, so it's easier to read off the graph. Let's do that. There we go. Here's my ball at the end. And we're going to make an assumption for this calculation that this ball is, you may see this on an exam once in a while. I'll say, you can assume it's a point-like mass. All I mean by that is that we can ignore the spatial extent of this thing, that the radius of the ball is small compared to L, the length of this. It doesn't have to necessarily be a point-like. So in other words, on this problem, I had a great question over here about the torque caused by that wire. In that case, you couldn't assume that that wire is essentially infinitely thin. There's no way to exert a torque then, right? So in that case, we really couldn't have made such an assumption. But here we're going to say, all right, I'm going to assume that the size of this thing is so small compared to the L, we can ignore the fact that it's, all we need to know is its mass, right? When we calculate the moment of inertia, all that matters is how far it is away from the pivot point. Let's use this as our pivot point, right? I always label it. And let's define this as theta. And this is important. I'm defining theta to be positive as I go this way. So whether I recognize it or not, you might not recognize it because it tripped me up a few times. You'll be shocked to hear. When I set this problem up in the past, if I go from here to here and call that positive theta, then I've already made a decision about my direction for positive rotations. I decided that they're going to be counterclockwise. So most, like in the problems you're going to see on Thursday, I don't think this issue will come up, but be aware of it in case it does. Usually with rotary motion problems and statics problems, we're just talking about acceleration, angular acceleration in the context of Newton's second law for rotations, right? But when we have problems like this, where we actually are going to specify theta, we're going to talk about your displacement from some equilibrium. So this is the equilibrium value for theta equals 0. And we're pushing theta, we're pushing the ball this way, right? We're moving the bowling ball one way or the other and saying what's going to happen. In that case, if we call this positive theta, we've made a choice about which way the positive sense of rotation, positive sense of rotation is. So stick with your convention. So if I'll do that, otherwise you do a minus sign and it won't make sense. All right, so good. So if I do that, now I can ask, what does Newton's second law for rotation say? Well, it says net torque equals I times alpha. And I'm referring now to the system I'm talking about is this thing, the string here, which is massless, and this mass on the end, mass M on the end. Okay. So what's going to cause a torque? Well, what are the forces acting on the mass? Let's see. Here's a free body diagram of my point-like mass. So now this is one of the few cases where my free body diagram for this mass anyway. I don't have to worry about the spatial extent of it. I'd say, okay, well here's my mass. There's gravity acting on it, mg. What else is acting on it? What are forces acting on the mass? Yeah, force of tension, right? The string's pulling up on it, so there's some angle like that, some tension acting on it. And I know that so the angle theta is right here. See that? I know that because it's alternate interior angles, and I also know it because I drew a picture with theta less than 45, so I can read it off. Easy to tell. Great. So my free body diagram, there's only two forces in the problem. If I want to know what the torque is, so which of these are exerting a torque on the system? My pivot point is up there. See that? Up at the top of the string. So does tension exert a torque on the system consisting of the string and this weight here? Why not? The force is pointing right at the pivot point, so it can't be exerting a torque. That's right. The only torque. So for the net torque, there's only one force that's doing it. It's the gravity force. And so to figure that out, I need to see. Oh yeah, there's some angle here. The angle's theta. You get that sine theta term with torques when you calculate them, right? So that means that the torque. Oh, and is it a positive or a negative torque? Gravity's pulling down, right? So mg is doing this. Tension's doing that, right? Is gravity causing a positive or a negative torque on the system? Negative. That's really important. And we got that right because we realized we defined it to be positive theta, so we get a negative torque. The restorative torque. Thank goodness. Otherwise, it would speed up faster and faster like that. Physically not what's happening, right? So good. We're getting something that makes sense. It says that we get a negative torque. What is the torque? It's the sine of this angle times the full length of the force vector and the distance vector. Here, I'll do it. Negative. So L is it's not the radial arm, right? The radial arm is L times sine theta. L is the distance, it's the full length of R, right? The vector from the pivot point to where the force acts. Mg is the full length of the force, and then we get sine of theta. Right? Does everyone agree with that? and that has to equal I times alpha. But what is I in this problem? Well, the moment of inertia of the system is easy to calculate. Doesn't require an integral or anything. It's just, and, you may be required to calculate something on the scale, right? So what is the moment of inertia of this system? It's just a point mass. You don't have to worry about the fact this isn't a sphere for us, because this is small compared to else. We can ignore the fact that there's a little, because the thing is, this does have a little bit of moment of inertia just by spinning, but it's not going to be very important compared to the moment of inertia from this, right? So we can neglect it. And we were told so in the problem. That I can choose as a point mass. Or we might also just say, here's my assumption. I'm going to say this radius is small compared to R, compared to L. So in that case, the moment of inertia is dominated by that distance and that mass being that distance away from the pivot point. So what is it? It's moment of inertia goes like what? Mass times the length? It's a mass times length squared. That's right. So I know that it's going to turn out to be, it is explicitly this mass times that length squared. That length being the distance from the pivot point to where the mass is. This is the sum of all, sum over I of m sub I times R perpendicular I squared. Well, there's only one item in the sum, it's this mass. And then we multiply that by alpha, right? But what is alpha? It's just the second derivative of theta with respect to time, right? Good. So now I've got my equation for this as a differential equation. But already I've wandered into nasty territory. This is a really hard differential equation to solve in general. Exactly. In fact, I think you have to use, there's named functions, I think, that are different than the basic sort of primary functions we deal with in this class. So the way we handle things like this is we assume it's use a small angle approximation. If I push the ball just a little ways, not very far, the angle that's formed is very close to 0. And it turns out that sine of theta, right, is well approximated by a simple function for small theta. So here's theta, here's sine of theta. This will be important this comes up all the time in physics classes. Certainly in rate B it'll show up with optics and stuff like that. But this right here is just the equation theta. So this is a line that goes through 0 with slope of 1. That's just theta. Sine of theta is well approximated by theta if theta is small compared to 1. And of course, theta is being represented here in radians, not degrees. This is not true for degrees. It's true for radians, right? So that's nice because it means that as long as we stick to small theta, then we can say, oh, sine theta is approximately equal to theta, and now we're back in business because now we have a differential equation we can solve, right? We've got negative L. Let's just go ahead and so look at this. The mass cancels out on both sides of this equation. L, one factor of L from here and one from here goes away. So already mass is gone from the equation. We simplified theta to sine theta to theta, so now we get negative g times theta. I substituted sine theta for theta here, and I substituted I got rid of these guys, and that equals what? It equals L times the second derivative of theta with respect to time. Okay, and now we get the single equation we solved several times now. The solution is sines and cosines, right? And in particular, when we ask what's the frequency of oscillation? Well, let's put this in the same form as the other equations here. Give me one more line. Let's go ahead and put this on the other side. You say theta equals negative L over G times the second derivative of theta. Okay, now we know what to do. Whenever we see something of this form, theta equals some constant with a minus sign in front times the second derivative of the same variable, whatever it is, doesn't matter if it's x or y or theta. The result is that this thing, that the square root of this thing is the frequency of oscillation. It's just same old math, right? So that means that the frequency of oscillation for a pendulum, right, is given by the square root of this, the square root of L over G. No mass appears there. You see that? Very interesting. So that means that, to me at least, so that means that the mass dependence of the oscillation here for a mass of a spring, it's very different, right? For a pendulum like this, the time it takes for the pendulum to swing through a full period doesn't depend on how heavy this ball is. So when Galileo was looking up at the ceiling, noticing all the periods were the same for all the chandeliers, no matter how big their amplitudes were. I actually should go look up, in fact, if he made this observation. I don't know if he did. It wouldn't matter how elaborate the chandelier was, as long as it had the same length, as long as it had the same length from the pivot point to the. You have a question? Did I do it backwards? I sure did. Did I? Well, let's think. I think I do it backwards. You're right. I took this thing. So I told you I was going to make that mistake. So what do? I check the units. So what are the units of this thing? Meters per second squared, and this is meters. So that's second. Oh no, that's clearly wrong because it gives me units of seconds, and units of 1 over seconds. And it's also wrong because bigger things they have smaller or bigger frequencies. Does that have a small frequency or a big frequency? Small frequency. Is L big or small? L is big, so it has to be a reciprocal relationship. You're absolutely right. I got it backwards because I did exactly the thing I warned myself not to do a few minutes ago. I solved this equation 3 times now in class. I got it right 2 times out of 3, which is not bad. Okay. Over here I had the square root of whatever. Oh, this was up here. Yeah, I got the kappa over I, and I said, oh yeah, whenever you have it in this form, make sure. Anyway, well, I didn't listen to my own advice. But right, it's 1 over this. In other words, it's this times you did an omega squared multiplying this and equals 1 over here. So that means if you put it on the other side, they equal square root. So good. Good. Now it's got the right units and it's got the right limits. So let me ask you this, brain teaser. At Stanford they have a two-story tall sort of pendulum set up like this. So it's not quite. I think it's about this high, maybe a little bit smaller. And they've got. It goes back and forth, and it's designed the way a lot of these things were built in the old days, before Stanford was built, in fact, a long time ago. People first built these to make clocks, right? And grandfather clocks have pendulum. Why is that? It's that over time they lose their energy and they get smaller and smaller amplitude. But when the amplitude shrinks to a very good approximation, as long as this is true, that you start off with a pretty small theta anyway, the amplitude, the period of oscillation doesn't change with amplitude. That's why you can build a clock with a pendulum. That's why people, when this was discovered, right, it was a huge breakthrough, because they could build timepieces that you could fall asleep, wake up, and tell you what time it is. You have to sit there and keep track of yourself, and it was accurate, even though it wound down. Most things, when the amplitude gets smaller, right, like a lot of things when they wind down, they slow down in a way that messes up their ability to keep track of time. But a pendulum naturally keeps the same period. But at Stanford, they've got this one, right? And it has the period that they like, but they want to tune it sometimes. Like they find it's a little bit slower, it's a little bit fast. They like to have exactly a certain period. So what they do is they stack pennies on it. And the pennies are very small in mass compared to the thing on the bottom. The thing that's swinging the pendulum is much bigger. So why does that make any difference for the period? I just told you that mass, this thing doesn't depend on mass. There's no m in this equation. The frequency of oscillation was the square root of g over L, right? Now that you got my head straight. So why is it that stacking pennies on top would affect the period of the frequency of oscillation? What is it changing? Which of these things is it changing, if either? Can it change g? Can you change the strength of gravity from the Earth by stacking pennies on top of this thing? No, it's always going to be 9.8 whatever it is meters per second squared. But what about L? What does L mean? What distance exactly is L? It's from the pivot point, but then what's on the other end of L? Yeah, it's the center of mass of the object. And we don't have to worry about that when we did this calculation because we assumed that this was a point like mass. But if you have an extended mass, then we want to figure out what L do we want? We want it to go from the pivot point to the center of mass of the object. If I stack pennies on top of this bowling ball, does that move the center of mass of the system? Did you still not have the pennies involved? Yeah, which way does it go? Up, down, right, left? Yeah, so if I put pennies on top of the bowling ball and say, okay, so initially the center mass is exactly in the center of the bowling ball, but then there's some screws on top. I forget that. Well, whatever. The center mass is wherever it is, very close to the center of that bowling ball. If I stack some pennies on top, what happens to the center mass? It goes up. So does L get bigger or smaller? L gets smaller. So if I stack pennies on top, L gets smaller. Does the frequency of oscillation go up or down? It goes up. If I keep stacking them on top, it's going to go faster. So if I want to tune this thing, if I want to have it, oh, it's not keeping, it's a little bit slow, put some pennies on top, and then it speeds up. And it's not because of the mass per se. It's because of the location of the center of mass, like this formula tells us. So that's, yeah, that's good. If that makes sense to you, that's good. It's a lot of ideas in a hurry. Okay, very good. We're almost through the stuff I wanted to get to. It's good because we're getting down to the 4 minutes. So let's see. What's the final thing? So the final thing I wanted to mention, well, I guess there's 2 final things. One is an obvious extension of what we just said. If we can make a pendulum out of anything. Like when I'm walking around, my lower legs act like pendulum, right? I mean, they swing around, and I'm also exerting some torques on them because of my muscles and stuff. But what I'm trying to get at is that, physicists of the world, they see all these masses on springs. They also see pendulum everywhere. There's all these things that have some rotation degree of freedom, but they're extended massive objects. But we could do the same treatment we did here, right? But instead of I being equal to L times whatever the mass is, there might be some extended object that's rotating about some pivot point. In that case, what we would do is we would just say, where's the center of mass, and then make L, as we just discussed. It's just that it might be more elaborate than just having a little bit of extent down here. It could be that this whole thing is a solid object that's rotating about a nail or something like that. In that case, find the center of mass of that object that's rotating, and then L is the distance from your pivot point to that center of mass. That's all. And then everything. Oh, and also you have to have some other way to calculate I. Then you have to be told what I is. But once you know that, then you can apply do the same thing. You'll get some other equation than this one when it all shakes out. But that allows you to use these ideas to deal with things other than the simplified case of just a string with a point mass on the end. Okay, so the final topic I want to talk about is the exchange of energy going on. So when you look at an oscillator like this pendulum, or for that matter, a mass on a spring, right? I'll just tell you. When you've got something that's going back and forth like this, the kinetic energy is greatest right at the center, right there, right? But then at the limits, at the extreme ends of it, that's when the potential energy, in this case, potential energy due to gravity. In the case of an oscillator, a mass on a spring, that's when the potential energy in the spring is maximal, right? And in fact, this is a closed system, right? I mean, you might say, well, wait, gravity's acting on it. That's true. But if we treat gravity as the potential energy of the system, it's a closed system, energy is conserved. It's just that it's being exchanged between different types of energy. And we can make plots of this. If we talk about, we've already plotted x as a function of time, we plotted v as a function of time, a as a function of time. We can also plot kinetic energy as a function of time, right? And if we do that, what do we find? Well, what is kinetic energy? It's 1/2 mv squared, right? Well, what is v? V looks like this. So let's take those pictures over there. V, I said, was a negative sine wave for that particular initial conditions I had. So here's what v looks like, right? So that's v. Well, what does v squared look like? Well, that means it's all positive for one thing. It also means that 0 squared is 0, negative a squared, or a times omega. Okay, so you get a squared, omega squared. Oh yeah, and I need an m. So there's an m times a squared times omega squared. Goes up to there, goes back to there, goes up to there, goes there. These have different units, so I'm just choosing arbitrarily to make the height the same. I'm plotting on the same plot, kind of weird. If you go through the math really carefully, it turns out that you get a sine wave, but it's a sine, or in this case a cosine wave, but it's one that's above the time axis everywhere. It's always positive, and it has twice the period, half the period. See that? The oscillations are occurring twice as fast. And that makes sense, right? You go through the maximum kinetic energy, the point in the middle, twice as often. You go twice per oscillation. So you start off over here, you go maximum kinetic energy. Maximum kinetic energy happen twice in one oscillation. That's what we find. Twice it happens. If we do potential energy due to gravity, or let's do the spring, what's that? Well, that goes, the potential energy due to the spring goes like 1/2 kx squared. And what does that look like? Well, x looked like this, right? It started up here, and it went down like that, and it went up like that. So that's x. If you do 1/2 kx squared, what you get? Well, you get this, right? And if you add these things up, they add to a constant everywhere. It's kind of magical, right? There's all these sine waves floating around, and you add them all up, and you check, and sure enough, it's true. The system has constant energy. Energy is preserved, is conserved, and it has that value I just typed right there, but you can write it a different way, too, by exchanging with all these other variables. There's lots of ways to write that same formula, that same quantity. Oh, anyway, so I'll let you guys go. But anyway, exchange of potential and kinetic energy. We'll do a little more of this stuff, and we'll do Q&A, too. If you have last minute questions about the exam, I'll answer questions Thursday as well.